Okay, let's start again. And so now we have Glenn Wagner that will talk about Kekule spirals in twisted bilayer graphene.
Okay, perfect. Hello, everyone. So today I'm going to be talking about Kekule spirals in twisted bilayer graphene. So this is some work I did during my time in Oxford with the following people here who are in Oxford and Berkeley. So, oh, no, this isn't working. Okay. So the content of my talk is as follows. I'll start by introducing the so-called Continuum model, which is the model for the band structure of twisted bilayer graphene that we're going to be using. And then I'll move on to talk about a certain limit of twisted bilayer graphene, the so-called strong coupling limit, where we can get some exact results. And then I'll show how there's some experimentally relevant perturbations that take us away from this strong coupling regime and introduce some new states, including this incommensurate Kekule spiral that I want to focus on. And at the very end, I'll just briefly explain to you how this fits in with a lot of the experimental observations that have been made over the past couple of years in this area. So let me start by introducing the so-called continuum model of twisted bilayer graphene, because that's going to be the basis for what I'm going to be talking about today. So you've probably seen slides like this many times before. Adi Stern was talking about twisted bilayer graphene as well last week in this conference. But let me just take you through it one more time so that it's fresh in everyone's memory. So I'm considering the case of twisted bilayer graphene, where you take two monolayers of graphene, stack them on top of each other, and twist them by some relatively small twist angle. And you can see that you end up with this sort of large periodic pattern, the so-called Moiré pattern, which is a periodicity which is much larger than the graphene unit cell, which is this microscopic length scale here. So what you've done is you've expanded the unit cell so that the unit cell is much larger than the microscopic graphene unit cell. And so what that means when you go to reciprocal space is that you've shrunk down your Brouwer zone. So on the right, I'm showing the two Brouwer zones of the two layers, one in blue and one in red. And then you're twisting them by the small twist angle relative to each other. And now that you stack these two layers on top of each other, you end up with this mini Brouwer zone, which is much smaller than the individual Brouwer zones. And so when you compute the band structure, you're going to have to compute the band structure folded back to within this mini Brouwer zone. And as you probably all know, the band structure of monolayer graphene consists of two Dirac cones at the K points. So here the K and K prime points of the microscopic graphene lattice. And so what you're going to do is you're going to take these Dirac cones at the K and K1 and K2 points of the two layers and plot them within this mini Brouwer zone, and then add some interlayer tunneling to get the full band structure of the twisted bilayers. So what that looks like mathematically is like this. I'm just writing down the Hamiltonian for twisted bilayer graphene. So this index here, 1, this is labeling the layer index. And I'm just writing down the different matrix elements of this Hamiltonian. So the diagonal part within layer 1 is just given by this Dirac cone, where the theta over 2 here is just indicating that I'm rotating the Pauli matrices by this angle theta over 2. And then in layer 2, I have the same, but twisted by the opposite angle. And then in addition to that, I need to switch on some interlayer tunneling terms where T1, T2, and T3 are these matrices in sublattice space. Yeah.
So you're getting rid of the two other per layer. There are two Dirac cones per layer. What happens to the other Dirac cones?
So that's right. So I'm just focusing on these two Dirac cones here, and then this this valid degree of freedom is just going to give me like a flavor degeneracy of 2, because I've got this flavor here and this flavor here, and I'm assuming that they're not going to talk to each other because they're well separated in momentum space, and in the low energy limit, I'm just going to care about the physics within one valley. Okay, so this is this form of the interlayer tunneling, and these T1, T2, T3 matrices are matrices in the sublattice space. Remember that this hexagonal lattice has got an A and a B sublattice, and so this WAA is hopping from the A sublattice of the top layer to the A sublattice of the bottom layer, and WAB is between A sublattice of top layer and B sublattice of the bottom layer. And in particular, there's a certain limit where I switch off the AA hopping, which is called the chiral limit, because in this limit, the Hamiltonian has an additional chiral symmetry. So this will be important later on. Okay, so this takes me to the so-called magic angle, because when you do this computation of the band structure, something interesting happens near this twist angle of around about one degree. So here on the left, this is this original paper by Bissett and McDonald, where you see the band structure for different twist angles, and you see that 1.05 degrees, these two bands here in the middle are extremely flat. And this is somewhat interesting because flat bands means we have high density of states, and so correlation physics will be important. And there's a way to compute this magic angle, just a very rough sort of scaling argument that I want to give to show you where this 1 degree comes from. So remember, we've got the 2 Dirac cones coming from the 2 layers, and the separation between these 2 Dirac cones is given by VF times theta over A. And then remember that I switch on the interlayer tunneling, which hybridizes these 2 Dirac cones. And so this term has size WAB. And so when these 2 terms are of the same order, the hybridization is going to be the same as the separation between the 2 Dirac cones, and this can result in flat bands if the sort of interference between these 2 effects is the right sign. Okay, and so furthermore, I'm going to just focus down on these 2 so-called central bands. So these 2 extremely flat bands that you saw on the previous slide. And I'm just going to neglect all the rest of the bands that you saw before, assuming that all the interesting physics is happening here, and we can check that indeed the other bands don't change the physics much. Yeah. No, so you see that they've got some finite dispersion, these so-called flat bands, but the dispersion is very small. You see that's a scale of a couple of MeV. But in a certain limit, this chiral limit that I talked about, these bands in fact become completely flat. But in general, they've got some small dispersion. Well, in the chiral limit, the way the wave functions look like are similar to the wave functions in the quantum Hall effect. So you get these sort of theta functions that you get if you do the quantum Hall effect on a torus. So yeah, they've got some more complicated structure, and in particular, they've got some non-zero churn numbers, these bands, if you gap out the Dirac cones. Okay, and so the physics we're interested in is all happening within these central bands. That's my claim. And what we're going to study is what happens as you change the density of electrons in the system, gradually filling up these 2 bands. So if you start with the chemical potential down here, and then via gating, increase the electron density until your chemical potential ends up here, you're sweeping from the left in this diagram to the right. Where this nu is the so-called filling factor, which is just telling you the number of electrons per Moiré unit cell. And the reason it goes from -4 to +4 is that, remember, I said before, we've got this Vallée degree of freedom. We've also got a spin degree of freedom. So that's this 4-fold flavor degeneracy. And we've also got two of these flat bands. So that gives us a total of 8 electrons per Moiré unit cell if we want to fill this entire band structure. Okay, and so on the right, I'm showing some experimental data that has been taken. So this is measurements of the resistivity as you change the electron density. And the interesting observation is that you end up with these peaks in the resistivity pretty much every time nu is an integer. So this is not surprising at -4 and at +4, because -4 and +4, your chemical potential is up here or down here, so you've just got a band insulator. But it's more interesting at all the other integer fillings, where just based on the non-interacting model, you would expect to get a metal. So clearly these are some sort of correlated insulators, and the question I'm going to try to answer today is what the nature of these correlated states is. And as I said before, if you just take the non-interacting model, you would just get a metal at all of these fillings. So we need to treat the interactions if we want to get some insulators. And so the model we use is combining this kinetic Hamiltonian I presented already with a standard Coulomb interaction piece, where the Coulomb interaction we use is some gate-screened Coulomb interaction, which is realistic for these experiments. And I just want to make the point that the interaction term also knows about the continuum model via the form factors that appear in this expression for the density. Right, so these form factors are just given by these overlaps of block wave functions, where alpha and beta here are band labels. And so the symmetries of this continuum model are going to be relevant for the interaction piece as well. Even if later on, I'm just going to throw out the kinetic piece, because I'm going to say that the bands are very flat, so the dispersion is small, so we don't need to care about it. So this takes me to the next subject, which is strong coupling phases. So as promised, I'm going to first of all completely throw out the kinetic term and just look at what the ground state of this interacting Hamiltonian is. And before I dive into to show you what happens for twisted bilayer graphene, let me just give you a little bit of intuition for what we might expect to happen. And in particular, we have two standard paradigms of strongly correlated physics, the Hubbard model and the quantum Hall effect. And both of these are relevant to the physics of twisted bilayer graphene. So I'll start by talking about the sort of connection to the Hubbard model. So this was thrown up very early on in the history of this field. You know, these first experiments in 2018 that showed that twisted bilayer graphene is superconducting also showed that you had these insulators that were close to the superconducting phases. And you can see that this insulator here is labeled as a Mott insulator. And this was because people thought about the analogy with the cuprate phase diagram, where you also have superconductors and insulators in close proximity as you change the doping. And so people thought that these two phase diagrams look rather similar. And so perhaps the nature of these insulating states is the same. It's also a Mott insulator as in the cuprates. I'll argue that that's not the case, but this was people's first guess. Now, if you want to write down a Hubbard model for twisted bilayer graphene, it's a little bit more complicated than you might imagine, because you've got this fragile topology as well, which presents an obstruction to writing down some localized Wagner states for the system. But it can be done. You can write down some tight binding model with some Wagner states, but in this work, they showed that the simplest Hubbard model you can write down has these Wagner orbitals that are localized on these three centers of this triangular lattice, right? And so this is going to mean that your Hubbard model is not just going to include some on-site interaction term, it's going to have some further range interaction terms as well. It's going to be more complicated than the sort of standard Hubbard model you might write down. And it's known that in this sort of case where you've got further range interaction, the Hubbard model tends to go to some sort of translationally symmetry breaking state, like charge density waves, spin density waves, or pair density waves. And for this reason, we might expect that translational symmetry breaking is going to be relevant for twisted bilayer graphene as well. and that's going to motivate us to look for translational symmetry breaking in our study. The second paradigm of strong correlation physics, of course, is the quantum Hall effect. And again, there's connections between twisted bilayer graphene and the quantum Hall effect. On the one hand, in experiments, people have observed this quantized anomalous Hall effect, where you see the Hall resistivity being precisely quantized to this h/e² unit. And furthermore, as I briefly mentioned before, in the Chiral limit, you end up with these exactly flat churn bands with wave functions that look just like the wave functions of the quantum Hall effect on the torus. And again, there's a certain limit of the quantum Hall effect where we find translational symmetry breaking, especially when you go to higher Landau levels, where the interactions are modified, and you get various striped and bubble phases. So basically, the point I wanted to make is that both in the Hubbard limit and this quantum Hall limit, we have translational symmetry breaking. And so this is a natural order to look for in twisted bilayer graphene. The second point I just wanted to make here, because it's going to be relevant for what I'm going to say next, is that in quantum Hall systems, because the kinetic energy is quenched, if we have some spin or pseudospin degree of freedom, you tend to get ferromagnetic states. So these states look something like this. K is just some momentum label, and the arrows are some pseudospin. And so typically, you end up with these quantum Hall ferromagnets when you've got some sort of pseudospin degree of freedom, where this is a ferromagnet where phi is just the angle in the xy plane in which these pseudospins are aligned. And indeed, we're going to find ferromagnetic states in twisted bilayer graphene as well. So let me now go, as promised, to this idealized limit of the continuum model. So if we just started with the continuum model as it is, it's got this U2 cross U2 symmetry, which decomposes as follows. So as I said before, we neglect tunneling between the two valleys. So spin is separately conserved in the two valleys, giving us these two SU2s. In addition, the valley charge and the electric charge is conserved, giving us these two factors of U1. So this is the full symmetry the model has, but now we're going to make two approximations which are going to enhance this symmetry class. So first of all, we neglect the single particle dispersion. So we pretend that the bands are in fact completely flat, in which case we have particle Hall symmetry. And then we're going to pretend that the wave functions are completely sublattice polarized, which gives us a chiral symmetry as well. Essentially, the Hamiltonian anticommutes with sigma z, where sigma z is the Pauli matrix in sublattice space. And together, these two additional symmetries give us this enhanced U4 cross U4 symmetry. And this is going to be this manifold within which we construct these strong coupling phases. And so just to represent this pictorially, remember I said with 8 flat bands, 2 flat bands which are each 4-fold degenerate, giving us a total of 8. And then I'm going to group them into these churn number +1 bands and churn number -1 bands, and they're labeled with the spin, valley, and sublattice labels. So spin, valley, and sublattice are associated with these Pauli matrices as well. And the U4 cross U4 symmetry is just allowing rotations within these churn sectors. And so now you see that this basically looks like 2 copies of the 0th Landau level of monolayer graphene, sort of 1 copy with magnetic field pointing in the up direction and 1 copy with the magnetic field pointing in the down direction. And as I said before, this will then motivate us to think about ferromagnetic states within these different pseudospin degrees of freedom. So just to present you sort of the energy scales on which these different symmetries are broken. So the largest energy scale is the energy scale of the interaction piece, which just includes the intra-sublattice interaction. And then there's these two perturbations that I mentioned before. There's the inter-sublattice hopping, which breaks the particle-Hall symmetry. And there's the inter-sublattice interaction, which breaks the chiral symmetry. And both of these break down the U4 cos U4 to individual U4s. And then finally, if I include the intra-sublattice hopping, then I break both particle-Hall and chiral symmetry and end up with just the U2 cos U2 of the continuum model. And so the name of the game is to find the ground states of this intra-sublattice interaction term, which we can find exactly, and then treat these two following perturbations in second order perturbation theory, and we're going to completely throw out the last term because you can see that it's an order of magnitude smaller than all the others. Okay, and so here are the strong coupling order generalized ferromagnets that I've mentioned before. So I apologize in advance. This slide is a little bit busy, but I promise you this is sort of the most complicated it's going to get. And I'll just take you through these different orders one by one. So the simplest ones to understand are these states that look like this quantum Hall state, where so I'm taking these four flat bands. I'm just assuming that spin is just polarized. I forget about the spin degree of freedom, and I just work within this sector of four bands now for simplicity. And I imagine that I want to fill two of these bands and think of the different possible ways I can fill these two bands. And the first way I could do it is just fill the two Chern number +1 bands. And this will give me this quantum Hall state shown here. But I could also fill the two K-valley bands, the two bands up here, and end up with a valley polarized state, which is shown down here. Or the third option is I could fill the two sublattice polarized bands on the B sublattice. So these sort of diagonal bands giving me the so-called valley Hall state. And then the final two states are called intervalley coherent states because they include coherent superpositions of the electrons in the two opposite valleys. So you're filling up electrons in the K and the K prime valley, and you're forming a coherent superposition of the two of them, where you can again think of this valley degree of freedom like a pseudospin, and then you're forming a ferromagnet in this pseudospin degree of freedom here. Okay, so this and you can do this intervalley coherence in two different ways. The KIVC state respects this T-primed time reversal symmetry, whereas the TIVC state respects the time reversal symmetry, like so. So tau x, remember, is the Pauli matrix in valley space. It's just flipping the valleys because the valleys are at opposite momenta, and K is just denoting complex conjugation, and this T-primed is just time reversal with some weird phase factors in there. And so this gives me two possibilities for this intervalley coherence. And on the level of the inter-sublattice interaction term, which was the sort of highest energy term in the Hamiltonian, all of these five states are exactly degenerate. You can show that they're exact ground states of this Hamiltonian. And to determine which is the true ground state, we need to add these perturbations in again. And these are these terms that I call J and lambda. So the J term is coming from this inter-sublattice dispersion piece. And the way it works is this inter-sublattice dispersion allows tunneling between these two Chern sectors, denoted by these red arrows here. And what this tunneling is going to do is, if you've got a state like the quantum Hall state, for example, it's going to allow tunneling between this band and this band, and via the standard Anderson super exchange argument, this will lower the energy of the state by an amount t squared over u, which I call j. And so indeed, you see that the quantum Hall state has lowered its energy by an amount j because it allows for this hopping between the bands. And similarly, for the Valley Hall state, you've got this hopping, which reduces its energy by minus j. On the other hand, the Valley polarized state doesn't allow for this hopping term, and so it can't lower its energy by taking advantage of this hopping. And similarly, you can show that the KIVC lowers its energy, the TIVC doesn't lower its energy when you include this j term. And then you can do the same thing for this inter-sublattice interaction piece and show that it increases the energy of the first three states by lambda and doesn't change the energy of these two states. And so finally, taking into account both perturbations, you see that there's one unique ground state, which is this KIVC state, which has energy minus j. So this is going to be the exact ground state of twisted bilayer graphene at integer filling of the Moiré unit cell. And so I'm now going to argue that when we add some additional perturbations to the Hamiltonian, in fact, it stabilizes a different kind of state, which I call this incommensurate Kekule spiral. And we get transitions between these Kekule spiral states and the strong coupling states as we tune certain parameters in the Hamiltonian. So what are these perturbations we're going to consider adding? So we start off with this sort of standard model of twisted bilayer graphene, which is just this standard continuum model. And we add three perturbations, the most important of which is strain. So experimental samples are known to be strained. And so this will break C3 symmetry and mirror symmetry and result in this sort of change in the band structure. And then we can also add terms to the Hamiltonian which break particle Hall symmetry, which is also known to be the case in experiments. And finally, we take into account the fact that these samples typically sit on top of a substrate like HBN, and the interaction of the twisted bilayer layers with the substrate is going to be important as well. So let me say a little bit more about each of these three perturbations individually. So particle Hall symmetry breaking, well, this is just one example of an experiment where you see strong insulators at positive fillings, weak insulators or no insulators at negative fillings. And in DFT calculations, this band structure is shown to be strongly particle Hall asymmetric as well. And basically, we use some terms motivated from this DFT to add to our Hamiltonian. Then strain is known to be relevant as well because you can just image the Moiré lattice in STM, and just by measuring the distances between these lattice points, you can basically measure how much strain there is in these samples, and the amount is typically 0.1 to 0.7% strain. And this explains something that was a bit of a mystery, which is the fact that there's a semi-metallic state at nu equals 0. So I showed you before the strong coupling state that was the KIVC state, and this is known to be an insulator. And so it was slightly mysterious that at nu equals 0, you didn't find this KIVC state. Instead, you found some sort of semi-metal. And in this Hartree-Fox study, they showed that if you add strain, this is the epsilon shown on the x-axis, you can actually destroy this KIVC state, which is this gap state on the left, and you end up with a semi-metal, which is this black phase on the right. So this, including strain, helps us understand why we don't get the KIVC state at nu equals 0. And then finally, the substrate potential. So HBN is has got the same hexagonal structure as graphene, but it's got inequivalent atoms on the two inequivalent lattice sites. And so it acts like a sublattice potential, in other words, sigma z in the Pauli matrix language. And so what it's going to do is it's going to gap out these two Dirac cones and give us two Chern number plus and -1 bands. And again, in experiments, it's known that whether or not you've got the substrate will influence whether or not you observe the quantized anomalous Hall effect. So it's known to be important. And so here's the main result I want to present, which is the sort of complete phase diagram of twisted bilayer graphene at all the different integer fillings. And on the x-axis, I'm always showing the strain between 0 and 0.3%. And on the y-axis, I'm showing the sublattice potential. And you can see that for small strains or zero strains, we find precisely these strong coupling phases I was presenting before. So we find the quantized anomalous Hall effect, we find the KIVC state, we find this IVC plus quantized anomalous Hall state. It's basically half of the KIVC, and the Valley Hall state as well. So these were all these strong coupling generalized ferromagnets. But then if we add strain to the problem, you see that in every case, we stabilize a different phase, which is this IKS state, which stands for incommensurate Kekule spiral, or at charge neutrality, we stabilize the semi-metallic phase that I mentioned before. And so the inclusion of strain takes us away from this strong coupling regime and stabilizes this new state, which I'll talk about in more detail now. And by the way, these are all Hartree-Fock results that we did with including Coulomb interactions with the Continuum model. And we allowed for any kind of translational symmetry breaking because, as I said before, we expect translational symmetry breaking to be relevant here based on these heuristic arguments for the Hubbard and quantum Hall limits. Okay, so let me talk about the two new states that we find with strain, this IKS state and the semi-metallic state. So the semi-metal is pretty easy to understand. You can just equally fill these four bands. There's no symmetry breaking. It's just a featureless semi-metallic state. This is just the state you would get if you just filled up the band structure with no interactions. But the more interesting state is what we call the incommensurate Kekule spiral. And this is a translational symmetry breaking state. And the way it works is that it includes coherence between all these different sectors in this band structure. So it includes coherence between opposite valleys, opposite Chern numbers, and mixes these all together. And it does so at a finite wave vector. So the expectation value of this intervalley coherent order parameter is only non-zero at some finite wave vector Q. Okay, and so I can explain to you the physical mechanism that leads to this sort of exotic state arising. And you can understand it just by looking, in fact, at the band structure, the sort of interaction renormalized band structure in Hartree-Fock. So here I'm plotting the band structure in the K and the K point valley. And so this is the K valley. You see it's got a high energy region here and the low energy region here in blue. And then the K point valley is just related to the K valley by C2. So it's just flipping this by 180 degrees. And as we saw in this strong coupling picture, it's favorable to form ferromagnetic states, in which case you want to form intervalley coherence between the K and the K point valley. And ideally, you want to do so in the entire Brillouin zone. But now you see that you've got this energy penalty coming from this peak up here and this peak up here. So ideally, you want to completely valley polarize in this region in the Brillouin zone. You want to fill up all of these low energy states here and all of these low energy states here. And you want to leave all of these energy states in the red region empty. And then you want to form coherence between all the remaining areas in the Brillouin zone. And the way to maximize the coherence between these two regions is to shift one Brillouin zone of the one valley with respect to the other by this amount Q, such that the low energy lobe of one region is aligned with the high energy lobe of the other region, and vice versa. So that in this region here, all of the electrons are in the K valley. In this region here, all of the electrons here in the K point valley. In this region here, all of the electrons are in the K valley. And in the rest of the Brillouin zone, you just let them form some intervalley coherence. And we can demonstrate this if you just look at the order parameter. You see that it's pretty uniform everywhere except at these positions of these lobes where the intervalley coherence is zero, because you're forming some valley polarized state by filling up these low energy lobes. And so now I should explain why we call it an incommensurate Kekule spiral. So the first word in this name that needs explaining is incommensurate. So the reason it's incommensurate is when we compute its dispersion relation, we just find this sort of curve that has a fairly shallow minimum at about 1/2 of the Brouwer zone, or 1/3 of the Brouwer zone. And this wave vector is not commensurate with any sort of lattice vector. It's just smoothly changing as you change these parameters of the Hamiltonian. And so in general, this spiral state is incommensurate. And I should add that if you compute the shape of this parabola here, you find that the stiffness corresponds to a BKT temperature of about 7 Kelvin, which is consistent with the temperatures at which these insulators are observed. And the second part of the name I should explain is, why do we call it a Kekule spiral? And the reason for that comes from looking at the real space picture of the state. So first of all, let me just look at this KIVC state, which is translationally invariant and includes intervalley coherence. So you're pairing up states with momenta close to the K and the K primed valley. And so in a way, you're breaking translations in this way. And this results in a tripling of the unit cell. You can show that if you connect the two valleys by a wave vector, this corresponds to tripling of the unit cell. And if you look at this tripling of the unit cell in real space, it gives you this sort of Kekule pattern, where you can see that if you go around this hexagon, around the black cross, you've got this sort of plus minus sign of the bond order parameter. I'm plotting here the order parameter CA dagger CB on each of these bonds, and blue means that the bond order parameter is positive, red means that the bond order parameter is negative, and you see that it's got this alternating sign pattern as you go around one unit cell. And then as you go around this unit cell, it's always positive. As you go around this unit cell, it's always negative. And so you see that you've got this tripling of the graphene unit cell that I mentioned before. So this is this Kekule pattern that reminds you a little bit of like benzene, for example. And so now when we go from the KIVC state to the IKS state, what we're doing is we've got this same IVC order, but it's spatially modulating. Or in other words, this Kekule distortion is spatially modulating. And so if I go from one Moiré unit cell to the next, what's happening is that this Kekule distortion is shifting, and that's what I'm plotting here. You see as you go from 1 to 2 to 3, the Kekule pattern is changing, right? If you go around the black hexagon here, you've got alternating signs. If you go around the black hexagon here, you've got the same sign, but positive. And if you go around this hexagon here, you've got the same sign, but negative. Okay, so this is the precise way in which translational symmetries are broken in this Kekule spiral state. And so here I just wanted to make a connection to what Christopher was talking about before, because we can come up with a sort of generalized LSM theorem for the state. Because even though it breaks translational symmetry, it actually preserves some modified translational symmetry. So if we have a translation plus a valley rotation by an appropriate amount, then this symmetry is satisfied. And so this gives us some generalized block theorem where K is now not the usual momentum, but it's this momentum that we shift by Q/2 in one valley and by minus Q/2 in the other valley. And in this sort of shifted momentum picture, we indeed just recover the usual block wave functions. And because of this generalized translation symmetry plus the U1 charge conservation symmetry, we've also got this generalized LSM theorem that tells us that this IKS state is only gapped at integer fillings nu, unless there's some additional topological or symmetry breaking order. And so indeed, if we look at some non-integer fillings, we find gapless states and no gapped IKS order. And so finally, let me just briefly mention how the state is consistent with all of the experimental observations. So in our Hartley-Fock calculation, we find a semi-metal at mu = 0 that's been observed in experiments. We find metallic states at ±1. I didn't mention it before. This hatching here you see in these phase diagrams, this is just showing you the gapless regions So all of these states are gapped except where there's hatching. And so at ±1, you see that the IKS state is actually gapless, which is consistent with metallic states that have been observed. We find spin unpolarized insulators at ±2, Chern-Ziegel insulators at +3, again, consistent with experiments. And finally, there's been an observation that the superconductivity that's observed between -3 and -2 is nematic. And so the fact that we've got a nematic state at -2 and at -3 is perhaps making it plausible that the superconductivity between these fillings should be nematic as well. If we imagine that the IKS state is the parent state from which superconductivity emerges, then it would be natural to imagine that it inherits this nematicity from the IKS order. And finally, is it possible to have direct experimental observations? So what I showed you before was, that our state is consistent with all experimental observations, but it would be nice if you could actually observe the translational symmetry breaking directly. And so there's a couple of signatures that one might look for. The first one is that the KIVC state is spin polarized at +2, whereas the IKS state is spin unpolarized. So if you could modify the strain to have a phase transition from the KIVC to the IKS state, then you would see a change in the magnetization coming from this change in the spin moment. So if you could have devices where you change the strain, you would observe this transition, hopefully. Of course, the most direct way to image the state would be to really see this Kekule pattern, which you might hope to do using STM. It's a little bit difficult because the electron densities involved here are extremely low, and so the Kekule pattern would be extremely weak. But perhaps this would be the most straightforward way to observe the state. And finally, it would be much easier to detect charge order than this Kekule pattern. And if you write down a Ginzburg-Landau theory for the state, you can show that the eccentricity of this IKS spiral state couples to charge order. And so if you can change the eccentricity of your state, you can introduce some subsidiary charge order, which would then be observable. So let me conclude here. So I've presented this new state that we found in our Hartree-Fock study of twisted bilayer graphene, which we've called the incommensurate Kekule spiral. It's a candidate for the insulators that have been seen at all non-zero integer fillings of the Moiré unit cell. It's stabilized by strain, which we know is experimentally relevant. And the state is a pseudospin spiral where pseudospin is coming from the valley degree of freedom, and it's generally at some incommensurate wave vector. And in real space, it looks like a Kekule distortion of the microscopic graphene lattice. Thanks for your attention, and I'm happy to take any questions you might have.
Nice cartoon.
I think we've got one question.
Here is a question. Yes.
Have you calculated the topological invariant directly in real space? Or so how will you quantify the topological number when you don't have translational symmetry? I was wondering how you, for instance, your Chern number that you show in the picture is calculated directly in real space through real space formula, or?
So this IKS state that I presented, it's got 0 net Chern number.
Yeah, but when you talk about in the sector, you have the two Chern sector, let's say plus and -2, no?
Oh,
I mean, it seems to me that there is an anomaly also in, I mean, in the picture where you have the strain, and then you quantify, you say, okay, I have the anomalous quantum hole, I have the Valley hole, means that in the anomalous phase, you are quantifying the Chern number, right? Somehow, even without translational invariance.
Yes,
and
yes.
This should be done in, I guess, in real space, this calculation.
Well, all of these states are translationally invariant.
Because of this generalized block theorem, or?
so the generalized block theorem is just for this IKS state.
Okay.
But all the other states that I presented here, all of these are translation invariant.
Right, but when then you have after this discussion about it that you break translational invariance, right?
For exactly.
Yeah. Okay. Yeah. Here. Yeah. Something. And then okay, then you say that you have already always this kind of generalized translational invariance. Always. So
even the IKS state has this.
I mean, even with some impurities or some extra strain that does not. So every time you have this block theorem.
Yeah.
I mean, I'm just asking because it would be, as I said, easier just to, calculate everything in real space and check at least for topological numbers, or
I mean, here what you do when you go down this generalized block theorem is once you've sort of shifted your momenta to this k prime momentum, which is shifted by plus q over 2 in one valley and minus q over 2 in the other valley.
I see.
Once you've done that, everything is just as
usual. Okay. So it's just
You can do all the same formalism and compute Chern numbers in this k prime. So you compute the Chern number, but instead of integrating over k, you integrate over k tilde.
And for the superconducting phase, do you use do you quantify the superconducting weight through the quantum metric, or from how do you?
So we've actually not we've not studied the superconducting phase.
Just because I saw the nematic superconducting order in one slide, so I was wondering if you had something.
So the nematic superconductor, yes.
Yeah.
So that's what's seen in experiments.
Okay. Was it just a discussion about directly in experiment? Okay, I see.
So in experiments, what you see is when you apply some critical field and destroy the superconductivity, and as you change the direction of the magnetic field, the critical field changes as you go around 360 degrees, and that's a sign that it's nematic superconductivity. But we've not actually computed.
Okay. I see.
Superconducting phase.
Thank you.
Can I ask a question?
Yeah, please.
So the Kekule order in the ordinary graphene, you can make a defect, and there's a fractional charge at the defect. Is this also the case for IKS state?
You want to make a defect in the order parameter of the IKS state.
Yes. Then can it accumulate some sort of charge?
Okay, so you're thinking about, for example, with the KIVC state, you end up with these skyrmions if you.
Yes, yeah.
Right. So in let's see, in this IKS state, I mean, in principle, you've got some order parameter in some pseudospin order parameter in your boson given by this given by the IKS state, and you could have defects in that order parameter as well. But I'm not exactly sure what that would give you. So we've not studied that problem yet.
I guess I think it can arise as you raise temperature, and then maybe near the BKT transition, we start to create defects, and then defects may or may not carry charge. But yeah, okay. So that's what I was wondering.
Yeah, okay. I guess this is what would happen in this. If you increase the temperature, then you'll get some BKT transition where your vortices unbind, and that destroys this the state at some finite temperature, which is presumably something like the 7 Kelvin that I showed here. Yeah.
Yeah, thank you.
So I had a plot of the density of states right at the beginning. Yeah, so here, this is just a plot of the density of states for the given band structure, and you see these flat bands give you this extremely large peak in the density of states close to zero energy. I mean, that's just coming from the fact that the bands are extremely flat, right? And your density of states is just proportional to 1 over the Fermi velocity, which is basically zero here. Yeah. So the Kekule pattern. I mean, like I said, the problem in seeing this Kekule pattern is that, well, Kekule patterns have been seen for monolayer graphene in experiments, but there you're talking about densities of electrons per graphene unit cell, whereas here you're talking about a certain number of electrons per Moiré unit cell. And so the Moiré unit cell it contains on the order of like 10,000 atoms. So you're talking about electron densities that are about 10,000 times smaller than for monolayer graphene. And so any Kekule pattern you get here is going to be much, much weaker than in monolayer graphene. And so seeing it is very difficult. I mean, if you're talking about sort of the validity of this sort of Hartree-Fock approximation, I mean, yeah, when we've computed these bond order parameters here, it's just taking our Hartree-Fock results and essentially just doing a Fourier transform to go from momentum to real space, and then this gives you this sort of Kekule pattern we're showing here. So that's a pretty straightforward calculation from our results.